Hello, this is Mr. Gilmore with the 8.4 Special Right Triangles lesson. Today you get to meet two very special triangles, the 45-45-90 and the 30-60-90. And you want to become very acquainted with these because when you reach Algebra 2 and pre-calculus, you're going to find that these two triangles are very important for you. With the special right triangles, we're going to find that there are some unique side relationships. And because of those unique side relationships, it's going to enable you to then see the importance of why these are here. We're studying these now, and also see the importance of them later when you get told a bigger story of mathematics in pre-calculus. So let me introduce to you the special right triangles. The two that we have in front of us are the 45-45-90 and the 30-60-90. Where the interest lies is really in the ratio of the sides. What we're going to find is that if we're given any one of the sides of these two triangles, we can find the other triangles based on just that one. So typically, though, in a right triangle, you'd have to know two sides to figure out a third. But with the special right triangles, you only need to know one side, and you can then find the missing links of the other two, because we're going to find that there's a direct relationship between all three sides of these special right triangles. And the one thing about these ratios of the sides is that the size of the triangle is irrelevant. For either the 45-45-90 or the 36-90, the ratio of the sides that we make are going to be the same regardless of the sides. And the reason why that's true is because of simple angle-angle similarity. We know that two angles of a 45-45-90 are equal to two angles of another 45-45-90, and we know that two angles of a 30-60-90 are going to be equal to the two angles of another 30-60-90, which means there is similarity between those two triangles. And because the sides because there is similarity, that means the sides are proportional, which means the ratios of those sides will be the same regardless of the size of the two triangles that are given. So we're going to start our adventure with the 45-45-90 right triangle. And the reason why it's called the 45-45-90, as you saw earlier, is that inside of it, it simply has the three measures of 45, 45, and 90. And what we're going to find, this is our very first relationship, what we're going to find with our 45, 45, 90, it again revolves around the sides. So you're going to see that we're going to prove something special about the sides of this triangle. Down below in the diagram, I do want to point this out first to you, that in our diagram we do see that we have triangle ABC, and we have the sides labeled with the lowercase letters. We have lowercase a, b, and c representing the side lengths. All right. Now in a 45, 45, 90, here's what happens. Here's what we're going to prove. And that's in our conditional above. So in a 45-49 right triangle, the legs are equal. So that's one thing we're going to prove. We're going to prove that the legs are equal. And that's actually a very simple thing to prove. We'll see that in our proof when we get to that proof in just a second. Very, very simple to prove the legs are equal. And there's a second part to this. And the hypotenuse, is root 2 times a leg, which means if you're given the length of any of the two legs, we know those two legs are going to be equal to each other. And if you want to find the hypotenuse very easily, very quickly, all you have to do is multiply that leg by root 2. So let's take a look at our given and proof statements. So in our given and proof statements, again, we start off with a 45-45-90 right triangle. And we're going to first prove that B and A are equal. Then we're going to prove that the two legs of the right triangle are equal. But then we're going to prove that C is really equal to the square root of 2 times A. Now, we could also have proved that square root of C is equal to square root of 2 times B, because in this case, we know that A and B are going to be equal. But that's going to be what we know, what we're learning to be special about the 45-45-90, is that if you're only given one side, you can find the other two sides without even having to touch the Pythagorean theorem. Now, of course, because it's a right triangle, and in our proof, we will use the Pythagorean theorem, so underneath the hood is still Pythagorean theorem. But what we find is that these side ratios will hold true anytime we encounter a 45-45-90 right triangle. So let's take a look at the proof of this. So here we have our same diagram, ABC, with the three angles labeled 45-45-90, and we have the three sides labeled A, B, and C. We're going to first prove that B and A are equal, and it's very simple. We can do that right off the bat. So let's take a look at our two column down below. We're given 45-45-90 right triangle. Well, that means we have two angles that are equal in measure if we have a 45-45 right triangle. Take a look at angle A and angle B. What do we then know if there are two equal angles in a triangle? We then know that the sides opposite of them are also equal. That's the converse of ITT, the converse of our isosceles triangle theorem. So immediately in step 2, we prove the first part of our proof statement, that B and A are equal. Now we're going to use that fact. We're going to use that B and A are equal as we now move into the second part of our proof statement, which is to show that C is equal to the square root of 2 times a. And really what the proof turns into is some more algebraic properties. So in step 3, we establish in step 3 that we know that a squared plus b squared is equal to c squared. So we use the Pythagorean theorem in step 3 to say that c squared is equal to a squared plus b squared. Now you notice I strategically set it up like that because I want my c variable on the left-hand side, just like I see it in my proof statement. But what I can do with that statement is I've just proven that a and b are equal. So look at from step 3 to step 4. Notice what I do. I take b squared out and replace it with a squared, which I'm allowed to do. B and a are equal in measure. And then I use substitution to simplify that. So I have c squared is equal to 2 times a squared. Take a look at there. Well, what can I do then with that? I can take the square root of both sides, so using the square root property, I end up with c is equal to the square root of 2 times a. And thus, in my very last statement, I prove the second part of my proof statement, that c is in fact equal to the square root of 2 times a. So what have we just done? We have proven that there's a relationship between all 3 sides of this given triangle. And I'm going to show you some examples here in just a second of where if you're given just one side of the triangle, the 45, 45, 90, then you can find all the sides of that 45, 45, 90 using this special relationship. So again, go back to what this theorem says, that in a 45, 45, 90, the legs are going to be equal, and the hypotenuse is any leg multiplied by the square root of 2. So let's do an example together. Here we have our triangle. Our triangle is again a 45, 45, 90. I see that. Well, we just proved that the 2 legs have got to be equal in measure, which means we're going to find our a variable very quickly. And then we're going to find our c variable by, again, taking any one of our legs and multiplying it by square root 2. So that's what we proved in our 45, 45, 90. So remember what our theorem says. It says that our legs are equal, and it says that c is equal to the square root of 2 times any one of our legs. It can be multiplied by a or b. Okay? Well, let's start with finding the missing variable a. Well, in our 45, 45, 90, the legs are equal, which means a is simply equal to 2. Why? Because our other leg is equal to 2. Thus, we found one of our missing variables. Very simple, very quick. Now, let's move on to c. To find c, we're simply going to take square root 2 and multiply by any one of our leg lengths. They're both measure 2, so it doesn't matter which one we pick. So we multiply by 2. I'm going to re-express that, just rewrite that as 2 root 2 is how I'm going to express my answer there. I like to put the whole number out front of the radical. And there we have it. There's our first example of finding the missing side lengths of a right triangle. Now think about that. Typically in a right triangle, just like we saw with our Pythagorean theorem lesson, we'd have to be given 2 sides. And with those 2 sides, we could then find a missing third side. But that's what makes this special, is we only need one side, and we can find the missing measures of the other 2 sides because of the special case of the 45, 45, 90. Let's do another one. This one's just a bit trickier because notice which side I'm giving you this time. I'm not giving you a leg to work with. I'm giving you the hypotenuse to work with first. So you know your c value here is equal to 4. You do know that a and b will be equal, which then that actually saves us a little bit of time. Because we know that a and b are going to be equal, if we find one of them, then we will inherently find the other value too. So now how are we going to find a missing leg? We'll go back to what our theorem says, okay? So our goal is, again, find what a and b are equal to, right? What are they equal to? So go back to what the theorem says. The theorem says that our hypotenuse is also related to the leg. It's c is equal to the square root of 2 times one of our 2 legs. Let's pick a, okay? I could say b, but let's just stick with a. Okay, so now I've got this. But what am I given? I am given that c is equal to 4. So think of this, what we just proved in our theorem, as an equation, which really what it is. It's a relationship between the leg and the hypotenuse, which means I can take the c value and replace it with the number 4, because that's what we're given. What does that leave us with? That leaves us with an equation that we can solve for our missing variable. This means we will have to divide both sides by the square root of 2. That cancels out. I'm going to kind of flip our equation around. I'll now have a is equal to 4 divided by square root of 2. This goes way back into chapter 7 when we practice simplifying radical expressions. I would like to rationalize this. So what I'm going to do is multiply the top and the bottom by the square root of 2. And this is going to clean things up for us. So in the numerator, I get 4 root 2. In my denominator, root 2 times root 2 by definition is just 2. And then we can simplify that because the outside numbers 4 and 2 have a common factor. And with that common factor, we just divide 2 out from both of those. So we end up with then 2 root 2. Now don't forget what we were just working on. We were working on finding the missing side measure of the legs. And we did it. We found our a value now to be 2 root 2. What does that mean about our b value? It's also 2 root 2 because our legs are equal. So there we have it. We worked backward from the hypotenuse to find a missing leg, again using what we proved in our 45, 45, 90 theorem. Now, before we move into the 30, 60, 90 right triangle, I would like to talk about adding some adjectives to our triangle. See, the thing is, in a 30, 60, 90, we are going to have two legs, and they are going to be different sizes. And we know they're going to be different sizes because of the converse of ATT. That if we know that one angle is greater than the other, then we'll know the side opposite is also greater, which is why we're going to apply some adjectives to the two legs of our 30, 60, 90. The short leg is the leg we will call opposite of our 30-degree angle. So you see down our diagram, the side opposite of our 30, we call the short leg. And we'll call the long leg then the angle, or the leg that's opposite of our larger angle, 60 degrees. We still have our hypotenuse here, so AB is still our hypotenuse, but we are going to need to apply some adjectives to the two legs of our 3690 because you're going to see that pop up in our conditional about what the 3690 theorem or right triangle theorem actually states. So you notice then I do reference each of those two legs with a new adjective, a short leg and a long leg, to help distinguish between those two legs. So now let's look into our 30, 60, 90 right triangle theorem. Again, this is a special case. Just like we saw with the 45, 45, 90, if we are given one side of this triangle, we can actually find all the sides of the triangle. And there's a little bit of a difference with the moving from the 45, 45 to the 30, 60, 90, not just because of the different angle measures, but in this case, everything revolves around the short leg. Okay, so the short leg is really the connection between all three sides. So we're going to find the relationship of the short leg to the hypotenuse and the short leg to the long leg. So the short leg is really the most important side of the 3690. If you're not given that one, which we'll do an example of that later, if you're not given that one, then the next leg you find is to find the short leg, because that's really what links all three sides together. So let's read what this conditional says. In the 30, 60, 90 right triangle, the hypotenuse is twice the short leg. So notice that, hypotenuse, twice the short leg. It's in relationship to the short leg. Simply, all we have to do is take the short leg and double it, and we get the length of our hypotenuse. And the long leg is root 3 times the short. So again, to find the length of the long leg, it revolves around knowing the length of the short leg. We multiply the short leg by root 3, and it turns into the length of the long leg. So down below, we have our diagram of triangle ABC with our 30, 60, 90 angles labeled. A is 30, B is 60, C is 90. And we've labeled our three sides A, B, and C. Now, what we're going to prove, and we're going to do it in this order, we're first going to prove that the hypotenuse is twice the short leg. So in other words, we're going to show that C is equal to 2 times A. Then our second part of the proof is we're going to prove that the long leg is equal to the square root of 3 times the short leg A. So again, both equations are going to revolve around the segment A, right? Because that's our short leg. Let's now dive into how we tackle this proof. Now, with the 45, 45, 90, it fell pretty much right into our lap. The 36, 90, we've got to do a little bit extra work to arrive to our conclusion, which you'll see the proof is a bit more extensive than we saw with our proof of the 45, 45, 90. So here's our proof. I know, wow, a lot to kind of absorb at first, but we're going to walk through this together. So again, we have our triangle up the top, triangle ABC, same diagram as before, 30, 60, 90 labeled. We've got our A, B, and C labeled. And we're going to prove in this order, first that C is equal to 2 times A, and then that B is equal to the root 3 times A. So where do we begin? We actually begin in this case with a construction. So here's what I'm going to do. Our protractor postulate allows us to measure and make measure. Now, I know that this angle C here measures 90 degrees. It's a right angle. So what I can do with the protractor postulate is actually cut that angle. So I'm going to construct a segment through our 90 degrees here. Let's see if I can make that segment a bit more straight. There we go. And we're going to cut that segment through our right angle. I'm going to call that point of intersection up at our hypotenuse there, M. Okay, so the M is on AB there. And the way I cut that is in a certain degree measure. I cut this so that this angle below, angle BCM, is 60 degrees, and the angle ACM is 30 degrees. So notice that's my first step here in the construction. Step 2, construct CM such that the measure of angle BCM is 60 and the measure of angle ACM is 30. Again, what falls into our construction category, I could be more specific and just say that's the protractor postulate. I'm allowed to measure and make measure. So I made some measure there by cutting that angle up into 2 smaller angle measures. Now, we're going to focus on first triangle BCM. So find triangle BCM in the diagram with me. We notice then that the angle at top, so we know the two base angles, or these two bottom angles, are both 60. Using Tasty, we can then say that this third angle here at the top, angle BMC, also measures 60 degrees, because all three angles have to add up to 180 degrees. What then does that make that triangle? It makes it an equiangular triangle, and we have a theorem that says if we're given an equiangular triangle, it's also an equilateral triangle. So in step 4 now, we know that all three sides are equal in length. So BC is measured as A, which means CM is measured as A, and BC is also measured as A. All three of those sides measure the same length as A. That's what we've stated there in step 4. But then in step 5, we continue that thought of, well, what else is equal to A? Is there another measure that's equal to A? And there is. Think about, now look at the triangle ACM. We have two angles that are equal inside that. Angle A measures 30, and the way we cut our right angle, it also measures 30, which means the opposite sides of those equal angles are also equal. That's thanks to the converse the isosceles triangle theorem. So con ITT again says that the sides opposite our equal angles are themselves equal, which then leads us to another conclusion that AM, that length there, also measures the length of A. So the way we designed our construction, we actually now prove that all those segments that were formed there are actually equal to the measure of A. Now take a look at the whole length of AB, which remember is our side length C. That's what we labeled it first, right? It's the length of C. Well, what is it now built out of? It's built out of two side lengths that measure A. So we finally prove here in step 6, our very first part of our proof statement, that C is actually equal to 2 times A, because if we add A plus A, the segment addition postulate says you can add the two parts that equal the whole. So that's what our reason is for step 6, segment addition postulate. We add the two parts that equal the whole. A plus A is equal to C, or really C is equal to 2 times A. So there we have it, our very first part of our proof statement. Now the last steps are going to turn a bit more algebraic. These last steps are going to lead us into the second part of our proof statement, that B is equal to the square root of 3 times A. So where do we begin leading into this last part? We begin with the Pythagorean theorem in step 7. Take a look at step 7. I know that since we were given a right triangle, I can apply the Pythagorean theorem. A squared plus B squared equals C squared. But we now know a new relationship about C related to side A. C is equal to 2 times A. That's what we proved just above, right? We proved that just in step 6. So in step 8, I'm taking C out of my Pythagorean theorem and replacing it with its corresponding equal counterpart, 2A. Now, when you take 2A and square, that means you also have to square the 2. So 2 squared is 4, and then A squared is just A squared. And that's what I'm doing in step 8, simplifying it. So now take a look at our equation here, the bottom equation here in step 8. It's two variables relating B and A together. So I'm going to subtract A squared off of both sides. So 4A squared minus 1A squared leaves us with 3A squared. So now I have in step 9, I've got B squared is equal to 3 times A squared. I can take the square root of both sides. Taking the square root of both sides, I result then in B is equal to the square root of 3 times A. And there we have it, our second part of our proof statement. So big picture, what did we just prove? We proved that in the relationship of our 30, 60, 90 right triangle, if we're given any one of the two of the three sides, we can find the missing links of the other sides. So think back again, with Pythagorean theorem, you needed to know 2 sides to find a missing third, but because of the special right triangle, we only need to know 1 side, and with 1 side, we can find all the other missing sides. So let's actually do an example of finding the missing side measures in a 30, 60, 90 right triangle. All right, so the very first thing you want to do when you dive into a 30, 60, 90 is remember your adjectives. Which is the short leg, which is the long leg, which is your hypotenuse. So the hypotenuse is easy one to spot. That is obviously the longest side, the one opposite of our 90. That's our hypotenuse, side C. The long leg is the side opposite of our 60 degrees, so this is going to be our long leg. And then our short leg is the one opposite the 30 degree, so there's our short leg. Now that I have that in perspective, I know what we've proven. We've proven that really the short leg is our A value, and this is what we proved in our 30, 60, 90 theorem. We proved that C is really 2 times our A value, and we proved that B is really the square root of 3 times our A value. So now, working with our short leg value of 3, plug in what we know. So I can find C very quickly. 2 times 3, simplify that, 6. So what is the length of our hypotenuse? Length of 6. Do the exact same thing over with our b value now. Plug in the value of 3. So it's 3 times the square root of 3. I'm going to re-express that with my whole number out front, and there we have it. There's my missing long leg value. Okay, so with our 3690 theorem, we only need one side, and we can find the missing 2. Let's move on to another example. So here's another. This one's a bit trickier. Okay, a bit trickier. So again, find your sides, label your adjectives. I know this is the hypotenuse, okay, automatically. This side here, down here with A, is opposite the 30, which means that's my short leg. And this is opposite of my 60 degrees, which is my long leg. Now, our theorem says that C, again, is equal to 2 times A, and B is equal to the square root of 3 times A. But notice what's different about this one. They didn't give us A this time. Remember, everything revolves around A. So how are we going to tackle this one? Well, we're going to have to work backward a little bit. If we're given the long leg, right, 6 is our B value. If we're given the long leg, then we have to first work backward to figure out our short leg. Then, using the short leg, we can figure out a hypotenuse. So remember, if you're not given the short leg first, find that short leg first. So if I were given the hypotenuse first, I'm going to work backward to find the short leg. If I was given the long leg first, such as in this example, I'm going to work backward to find the short leg. So now what I'm doing is taking this equation here that relates my long leg and short leg, B and A, and I'm going to plug in 6 for my B value and solve for A. So I'm going to have to divide both sides by the square root of 3. Doing that, again, I'm going to flip my equation around. I get A is equal to 6 over root 3. Well, I'm not going to leave it like that. I need to rationalize. So I multiply the top and bottom by root 3. I get 6 root 3 over 3, right? Because root 3 times root 3 by definition is just 3. And then notice my outside numbers. They simplify. 3 divides into 6 2 times with that root 3 still stuck on the end. And so there is my missing value of our side of A. A is equal to 2 root 3. So I come over here, and I think of my A value now as 2 root 3. That's what A is equal to. Now that I have my A value, it's going to make finding my C value a cinch, because I just come up here, I plug in what I just learned about my A value. It's 2 times the 2 of 2 root 3, and then I can multiply my outside numbers together. I get 2 times 2 is 4. The root 3 just tags along on the back, and there we have it, our missing hypotenuse, 4 root 3. So you are going to, in this little bit of tricky case, have to work backwards sometime to find your short leg, right? You're not always going to be given the short leg. So first, find your adjectives, find your sides, label them, and then work with what the theorem is, we proved about the theorem with the relationship of those 3 sides. Now, this last slide is kind of a pictorial summary of what did we just learn about these 2 triangles. Well, we learned that there is a relationship between all 3 sides of any given triangle, the 45-45 or the 30-60-90. In other words, if you take a look at these two diagrams below, what we see is that I've labeled now, instead of with specific numbers, I've labeled them with a variable x. So if I'm working with the 45-45-90 and I know the leg measure is equal to x, then I know the other leg, since they're equal, is also x, and I simply multiply the leg by root 2, and it gives me then the hypotenuse, right? So I can, with just one side, find the relationship of the other 2. Same story in my 30-60-90. It all revolves around our short leg. So if I was given the short leg as being x, that means to find the hypotenuse, just simply multiply by 2, and to find my long leg, I just simply multiply by root 3. So again, everything is connected, and we've proven that with these special triangles, all we need is one side, and we can find all the other sides of the given right triangle. So please be sure to hop over and take a look at the 8.4 worksheet and working with that with our special right triangles 45-45-90 and the 30-60-90. If you do have any questions on that worksheet, just email me and I will get back to you. With that, be good and do good.